Welcome to my presentation. In this presentation, let us try to solve system of linear equations in three variables using Gaussian elimination method. Let's say we have an example of this type. In this example, the system of linear equations are of this type: x plus 2z is equal to 5, then 3x minus 2y plus z is equal to 8, and then negative 2x plus 2y minus z is equal to negative 3. Let's call this as equation 1, call this as equation 2, and let's call this one as equation number 3. As step number 1, we're going to write the augmented matrix down for the given equation, for the given system of linear equations. So the augmented matrix would be as follows: the coefficient of x is 1, the coefficient of y, since there is no y, the coefficient of y is 0, the coefficient of z is 2, and the constant number is 5. Similarly, coefficient of x in the second equation is 3, coefficient of y is negative 2, coefficient of z is 1, and the constant number is 8. And in the equation 3, the coefficient of x is negative 2, coefficient of y is positive 2, the coefficient of z is negative 1, and the constant number is negative 3. Okay, so we'll put a line indicating that is the line separating the constant terms. So our goal in here is to be able to achieve a matrix where we will have ones along the major diagonal and then zeros below the diagonal. So we want to achieve this matrix. We want to have 1 A, B, C, and then 0, 1, D, E, and then 0, 0, 1, F. So let me explain this. We want ones along the major diagonal, and then we want zeros below the diagonal, and then whatever terms comes as A, B, C, D, E, F, those are based on the row operations which we're going to perform. Okay, so let us try to achieve that in this particular problem. Okay, so if we were to look at this, we want to make this location 0, that location 0, and to do that we're going to look at the second row. Let me write that here. The first row will be 1. Let me clear this out. The second row, I'm looking at second row, and if I were to perform the second row operation, the new R2 can be obtained as negative 3R1 plus R2. In here, negative 3 times 1 plus 3 will be equal to 0. Negative 3 times 0 minus 2, that will be equal to negative 2. Negative 3 times 2 is negative 6, plus 1 will be negative 5, and then negative 3 times 5 is negative 15. Negative 15 plus 8 will be negative 7. And then in the first row we have 1, 0, 2, and 5. And in the third row we have negative 2, 2, negative 1, and negative 3. Okay, so let me put a line here. So we've got the first step done, and then let's keep going. We want to have a 0 in this location. We want a 0 in that location. So to achieve that, we're going to look at the third row. We're going to look at the third row and then write it out in this manner. The new R3, let me write this a bit more clear. The new R3 is going to be as 2R1 plus R2. That should be able to give us a 0 in that location. So we'll come back and then complete row 1 and row 2 in a minute. So 2 times 1 minus 2, that will be 0. And then 2 times 0 plus 2, that will be 2. And then 2 times 2 is 4. 4 minus 1 is equal to 3. 2 times 5 is 10. 10 minus 3 will be equal to negative 7. And in the first and second rows, we did not modify anything. So therefore, those numbers are 1, 0, 2, and 5. In the second row, we have 0, negative 2, negative 5, and negative 7. So let's put a line separating the constant numbers. So we've achieved 0 in that location. So let us draw a line here each time to see where we are on the finish line. Okay, so we have some more work to do. We want to get a 1 in this location. So to achieve that, we're going to do a row operation, and to be able to get that, we're going to take the existing row 2 and then divide it by itself, divide by negative 2, sorry. So we'll first complete that operation and then come back and write the row 1 and row 3 above and below that. So 0 divided by negative 2 is 0. Negative 2 divided by negative 2 is a positive 1. Negative 5 divided by negative 2 is 5 over 2. And then negative 7 divided by negative 2 is 7 over 2. This is 2. And then the row above that is 1, 0, 2, 5. And the row below that is 0, 2, 3, negative 7. Okay, now let's draw this line along the major diagonal to see where we are. We wanted 1s there. We want a 0 in this location here, and let's keep going. So to get a 0 there, we can do a row operation on the third row, and to do that we can do this as follows. Row 3, the new R3 is going to be equal to negative 2 times R2 plus R3. That should do that. That should be able to get that. Negative 2 times 0 is 0 plus negative 2 times 0 plus 0 will be equal to 0. Negative 2 times 1 is negative 2 plus 2, that will make it 0. Negative 2 times 5 over 2 plus 3 will be negative 5 plus 3, that will be equal to negative 2. And then negative 2 times 7 over 2 plus 7. So negative 7 plus 7, that will make it equal to 0. And the rows above that, the first row we have 1, 0, 2, and 5. And in the second row we have 0, 1, 5 over 2, and then 7 over 2, like that. And then we'll put a line there separating the constant numbers. And then if we were to draw a line along the major diagonal, we have zeros below the diagonal, and then we want to be able to get a 1 in this location. Get a 1 in that location. So to get a 1 in that location, we're going to do some more operations in here and then see what we get. So to get a 1 there, we're going to look at the new R3. The new R3 is going to be equal to the existing R3 divided by negative 2. That should be able to give us the value we are looking for. 0 divided by negative 2 is 0. 0 divided by negative 2 is 0. Negative 2 divided by negative 2 is positive 1. 0 divided by negative 2 is 0. And the rows above that is 1, 0, 2, 5. And then we have 0, 1, 5 over 2, and then 7 over 2. And therefore, if I were to come back and then draw this line here, we have achieved 1s along the major diagonal, and we have achieved zeros below the diagonal. Therefore, from here we should be able to read this as follows. We can write from this augmented matrix, we can come back and then write the system of linear equations and then be able to solve for x, y, and z. In here, we can write this as follows: x plus 2z is equal to 5. There is no y there, and y plus 5 over 2z is equal to 7 over 2, and the value of z is equal to 0. The value of z is equal to 0. And therefore, when we plug it in, when we back substitute the values of z into this second equation and into the first equation, we should be able to go find the values of y and then the values of x. So since we have the value of z, we can find the value of y, and the value of y is going to be equal to, by substituting into the second equation, y plus 5 over 2z is equal to 7 over 2. If z is equal to 0, the value of y is going to be equal to 7 over 2, and that is one solution. And then again, in the first equation, if x in the first equation, when x plus 2z equals to 5, when z is equal to 0, the value of x is going to be equal to 5. So therefore, the solution for this system of linear equations in 3 variables is x equals to 5, y is equal to 7 over 2, and the value of z is equal to 0. This is the way we can solve the system of linear equations using Gaussian elimination method to arrive at the solution. We can also write this as a column matrix with unknowns like this: x times 1, 0, 0 plus y times, let me write this a little bit more clear, plus y times 0, 1, 0 plus z times 2, 5 over 2 and 1. That should be equal to 5, 7 over 2 and 0. So the question we have is, what combinations of what values of x, y and z should we have to be able to achieve the values on the right hand side as 5, 7 over 2 and 0. The values of x, y and z we have just determined to be equal to 5, 7 over 2 and 0. Those are our solution values. Okay. A system of linear equations in 3 variables can be represented graphically as 3 planes in 3 dimensions, or 3-dimensional coordinate system. So if I were to graph it out, so it could be represented in 3-dimensional graph like this. If that is x, and if that is y, and that is z, we can each one of these will represent a plane. Each one of these rows will represent a plane, and if we take 2 equations, they will represent 2 planes, and when plotted together they will meet in a line. So these could be, each one of them can be represented as a plane like this. I'm going to just draw something here that could be a plane like that, and then maybe I'll draw another plane that could be another plane like that, and then there could be another plane like that, and then all these 3 will intersect at a point, and since we have 3 equations, these 3 planes will be the point of intersection of these 3 planes will be x, 7 over 2 and 0 in this particular in this particular case. So in my next presentation we shall look at some more examples as to how we can solve system of linear equations using some advanced methods.